Hi everyone, today we're going to look at how to solve heat equation or a parabolic type equation given in an zero boundary condition. So consider the heat diffusion equation. So this is a heat equation. The heat equation is example of one parabolic type equation given by ut equals to alpha squared uxx. Okay, so we are going to look at zero boundary condition where u at 0 t is given by 0 and u at lt given by 0 as well. U at x naught given by fx. Okay, where our x is defined from 0 to L and t is greater than 0. So this is called the boundary condition, and when t is 0 we have the initial condition. Okay, so we want to solve this on a zero boundary condition. Okay, now let's recall the heat equation. We know that our solution is uxt. This is the temperature. Okay, temperature at position x at time t. Okay, and what is we wanna know that the L is, this L is the length of the rod, and F can be any function. Okay, so we want to show that this heat equation can be solved using separation of variable. Okay, to do that, okay, let's introduce the product sum of given by u at xt is given by big X, product of big X and small t, where this X is a function of X alone and t is a function of t alone. So we want to solve this problem, right? ut equals to alpha squared uxx. So differentiate this respect to t. Ut will give me t prime t. Now differentiating with this respect to x will give me x prime x tt, and differentiate the second time will give me x double prime x tt. Okay, substituting into the equation, ut equals to alpha squared uxx. This is the heat equation we want to solve, gives you big X t prime t equals to alpha squared uxx x double prime x tt. Okay, by separating the variables, we have t prime over tt, okay, equals to alpha squared x double prime x over, okay, now ignoring all the inside term will gives me t prime, sorry, I want to ignore all the inside term. That will give me t prime over this alpha, bring it here, equals to x double prime over x. Now for this inequality, for this equality to hold, we must have this is equals to k, where this k is the separation constant. Okay, so now we have two equation, two ODE. The first one is given by t prime over alpha squared t equals to k, and the second one, x double prime over x equals to k. So we want to solve this equation equals to 0. So the first equation, I have t prime minus k alpha squared t equals to 0. This is equation number 1. And the second equation, x double prime minus kx equals to 0. This is equation number 2. Okay, we need to so we want the separation constant k to be negative. Okay, so what do you want? We want this k to be negative, so that the solution for tt goes to 0 as t approach infinity. Okay, for this reason, we will let k equals to negative lambda squared, where lambda is non-zero. Okay, now equation 1 will become we have t prime plus lambda squared alpha squared t equals to 0. This is the new equation, and the next equation will be x double prime plus lambda x equals to 0. This is the new equation. Now, how do we solve this? Okay, solving for 3. Let's solve for 3. So this is first order, right? So the first order equation, or we can actually use solve this as t prime equals to negative lambda squared alpha squared t. T prime over t equals to negative lambda squared alpha squared. Remember, this big T depends on small t. So when I integrate this, so I have ln t equals to negative lambda squared alpha squared small t respect to dt. Taking the exponent, lambda squared alpha squared t. So therefore we have, for the t, don't forget I have a constant plus c, so I have a e negative lambda squared alpha squared t. Okay, this is solving for equation 3. Now similarly, we want to solve for equation 4. Solving for equation 4, we'll call this equation 5 now. So equation 4 is given by x double prime plus lambda squared x equals to 0. Now this is second order equation. So we use the characteristic equation given by m squared plus lambda squared equals to 0. M squared equals to negative lambda squared. Okay, now solving for m. So m will be plus minus lambda I. So we have the complex form. So if you have m equals to plus minus alpha plus beta I. Okay, your solution will be, if you recall, your solution will be exponent alpha x a sine beta x plus b cos beta x. Okay, this is the general solution. So similarly for this one, my alpha is 0, but we only have beta. So the solution for this will give me x of x, okay, equals to a sine lambda x plus b cos lambda x. Okay, this is my equation number 6. Okay, so since we know that, what we know? We know that we are given uxt equals to, earlier on we have defined this. So this gives me a sine lambda x plus b cos lambda x with my t, my equation number 5, which is exponent negative lambda squared alpha squared t. You don't have to define another variable there like a or b because you already have a constant. Okay, so this is my uxt using separable variable. Now, if given the initial condition, so what's the initial condition given? Okay, first we have the boundary condition. We are given u at 0t equals to 0. So when x is 0, when my x is 0, I have lambda squared alpha squared 3 a sine 0 plus b cos 0 equals to 0. So this gives me exponent negative lambda squared alpha squared t b, because cos 0 is, this is 1, 0. So therefore my b equals to 0. And then the second condition is given by ULT equals to 0. So we have e negative lambda squared alpha squared t. When x is out, I have a sine L lambda, because my b is already 0, equals to 0. So sine L lambda equals to 0. Now L lambda will be, what gives you sine 0? We have plus minus pi, plus minus 2 pi, plus minus 3 pi, and so on. So we will say L n is plus minus n pi, because this is n is 1, n is 2, n is 3. So this gives me lambda n equals to plus minus n pi over L. So we cannot say a equals to 0, but we choose that we will have the solution. So therefore our solution unxt equals to an e negative n pi alpha over L squared t sine n pi x over L for n equals to 1, 2, 3, and so on. Okay, so we can also have the summation sign for this. Okay, in my next video, I will show you how to find the solution for an. That's all for today.